So, dear students, I hope everybody is fine, and we are discussing operators, and we are discussing the commutation relation between the operators. In this video, I'll be talking about the commutation between the operator, the position operator x cap, and the momentum operator p cap. And in general, I mean, in quantum mechanics, the commutation relation between position uh, and momentum operators is really fundamental, and it certainly plays a crucial role in theory. So let's try to obtain the commutation relation between position and momentum. But before that, it would be rather right to start with these operators. I mean, in position operator, suppose we have a position operator x cap. Uh, this position operator x cap, it acts as a multiplication by x, and so to say that this x cap operates on the wave function psi of x. So if it operates on the wave function psi of x, what we obtain is x psi of x. So x will come up as the eigenvalue for the position operator. And similarly, we have a momentum operator. So this is our position operator, and we have a momentum operator. Momentum operator. And this momentum operator is p cap, and p cap is, by definition, it is minus ih cross d by dx if we are choosing one-dimensional problem along x, where this h cross is called reduced Planck's constant. It's called as this h cross is reduced Planck's constant. So we have a position operator, and this position operator can be operated on the wave function psi, and we have momentum operator, and this momentum operator can also be operated on the wave function psi. Now, what is our aim in this video is to obtain the commutation relation, which is very fundamental in quantum mechanics because it certainly has a kick in Heisenberg's uncertainty principle. So to find the commutation relation between x and x cap, which is the position operator, and p cap, which is the momentum operator, what we need is we need to compute the commutator of x and p. So we have x cap and p cap. And this is defined as x cap p cap minus p cap x cap. Now let's try to solve this problem step by step. And what we have here is we have the first term is x cap and p cap. So in this case, we would like to operate this x cap p cap on the wave function. We'd like to operate it on wave function, say psi of x, that we have predefined. So what we will have x cap p cap operated on psi of x. So if I keep x cap out, then for p cap, see, order is important. This p cap, I will write its operator. I will write momentum operator, that's minus ih cross d by dx of psi of x. So x cap p cap is going to give us minus ih cross x d by dx of psi of x, because the position operator on psi, it's going to give us x. Now, so this is our x cap p cap. Now we would like to have another action, the action of p cap and x cap on the wave function. First, what we did, we acted x cap p cap on the wave function. Now we would like to act, so I'll call it 1. So we would like to act, now we would like to act p cap x cap on psi of x. So this will be p cap times x cap and psi of x. So x cap will operate on wave function psi of x. So we'll have p cap x. Now it's not an operator because this operator has acted on wave function, so we have got x. P cap x and psi of x. So what we expect here, we would like to write down the momentum operator. So what's that? That's minus ih cross d by dx of x psi of x. So suddenly everything is visible to us. We can go for UV rule here. So this x will act as u and psi of x will act as v. So what we will obtain here is we will obtain here minus IH cross, and psi of x as its differentiation of x will give us 1, then minus IH cross x as its the differentiation of d psi of x by dx. So what we have two things. I would like to call this as equation 2. So we have x cap p cap, we have calculated it, and we have p cap x cap, we have calculated it. So now we would like to write down the commutation relation between x cap and p cap, because that's equal to x cap p cap minus p cap x cap. So x cap p cap is this much. So what's that? So now we'll be looking for the commutation relation. So what we will have here is we would like to subtract the 2 that we have obtained. In the left hand side we have the commutation between x cap and p cap. So that's going to be equal to minus IH cross x d by dx of psi of x, then minus, okay, then minus IH cross of psi of x, and then again minus. So this is minus times minus, then we have minus IH x d psi by dx psi of x. And we can clearly see that this term and this term will cancel. This is minus minus, this will give us plus. So the commutation between x and px will give us IH cross psi of x. And we can write down the commutation as x cap p cap. So here I have acted upon on psi of x, and if I have acted upon psi of x by x cap p cap minus p cap x cap. So what is this? This is the commutation. This is the commutation. So I have acted this commutation on psi of x. So the commutation between x and px is simply IH cross. Now, so what we have obtained is x and p, which is again px. The commutation between x and px is simply IH cross. And in 3 dimensions, the position and the momentum operators and their commutation relations. So we can write down the commutation relation in 3 dimensions. So what can we do here is if we take some ith component of position x I cap, and some jth component of position sorry, not position, momentum p cap as pj, then the commutation between xi cap and pj cap can be written as IH cross delta ij. This means if I is equal to j, then we will have xi cap p I cap. This commutation is going to give us IH cross. So they don't commute. And if I is not equal to j, that means xi cap and pj cap, this is going to give us 0. So these commutation relations are crucial. They are important. They are essential for understanding the uncertainty principle, where they imply that more precisely one measures the position, less precisely one can measure the momentum, and vice versa. So dear students, here we are going to obtain the commutation relations among the orbital angular momentum components, and we can start with the definition of orbital angular momentum as suppose L is the orbital angular momentum. It's defined as the cross product of R and the linear momentum P. And we can write down this r as the position vector in terms of Cartesian coordinates as xi cap plus yj cap plus zk cap. And for momentum, the linear momentum, we can write down, because this momentum is the momentum operator. So we would like to this operator in terms of its components as p cap x I cap p y cap j cap and p z k cap. So we can resolve this cross product between r and the operator, the components of operator of the linear momenta, by evaluating simply the determinant. So L will give us this is I, J, and K, then X, Y, and Z, then PX, PY, and PZ. And we know how to evaluate this determinant. So what we will have here is I, so we can cut it out. So we will have YPZ minus ZPY. So then this one will be minus J times, so this will go, so XPY minus YPX, and then K, for K we'll cut these two and we'll have plus K times XPY minus YPX. So in the left hand side we have L, and we can write down this L also in terms of its components, and what we will obtain is we will have Lx I cap plus Ly j cap plus Lz k cap. So this is equal to, yeah, this is I times ypz minus z times py. Then we have minus j times xpy minus ypx, and then we will have plus k times xpy minus ypx. So this equation can be true only if the coefficients of I, J, and K are equal. So here we can write Lx is it is ypz minus zpy. All right, and Ly we can write as so this is minus times xpy minus zpx, and then Lz will be xpy minus ypx. What is important here is that we have to keep in mind that this P is the momentum operator, so everywhere we have the caps. Px, Py, Pz, they are the components of momentum operator. So so we can also write down this as, if I use the operator for the momentum, and what we will have is we will have, if I get minus out here, it will be let me, so this PZ will have its component as minus IH cross dou by dou Z, and this will have minus IH cross dou by dou Y. So I think minus IH cross will be out, so inside we will have Y dou by dou Z minus Z dou by dou Y. And for this y component of orbital angular momentum we will have, so So minus IH cross will come out. That minus will become positive with this minus. So we will have IH cross times Z dou by dou X minus X dou by dou Z. Okay, and for the Z component we will have minus IH cross times X dou by dou Y minus Y dou by dou X. So these are our components of orbital angular momentum. Lx, this is Ly, and this is Lz. Now, what is our motivation? What's our goal here? The goal is basically to obtain the commutation relation between Lx, Ly, Ly, Lz. So let's take the first commutation relation and try to go for it. So we will start with say the commutator of Lx and Ly. So when we open it, what we write Lx cap, Ly cap plus Ly cap and Lx cap. So we would like to see that what will be the result of the commutation between Lx and Ly. That's our motivation. So so from here, what we will do is we would like to take on this part, that is Lx and Lx and Ly. So we have Lx Ly and we have Ly Lx. So we have to solve for Lx Ly. Then we will solve. This is not plus here. This is minus. Then we have to solve for Ly Lx. So to start with, it is better to first write down the result of this commutation Lx and Ly is IH cross Lz. So this is our target. We have to obtain the commutation between Lx and Ly, and this commutation results give us IH cross Lz. So so if I take on that equation again, this Lx and Ly, this is simply Lx Ly minus Ly Lx, and I would like to operate this commutation relation with psi, make an action on psi, and psi is the wave function. So so when we do that, what we will have here, Lx cap, then we will have Ly cap, and then we will have psi minus, then we'll have Ly cap, Lx cap, then we will have psi. So we would like to evaluate this part and then evaluate this part and subtract the two parts, and that should give us the result that the commutation between Lx and Ly is simply IH cross Lz. So we would like to take this Lx, Ly, and psi. So what it will be, so Lx and Ly, we have already evaluated that. We have Lx and we have Ly. So we can write down this as minus IH cross times Y dou by dou Z minus Z dou by dou Y times then we will have Ly. What is Ly? That is IH cross. So IH cross times, yeah, then Z dou by dou X minus X dou by dou Z. So this whole thing is multiplied by psi. Now all we have to do is to distribute the terms. We would like to maintain the order, but we have to distribute. We would like to multiply this with the first term, and then this with the second term, then this with the first term, and this with the second term. And I think this this IH cross and minus IH cross, these two terms will come out. So I can write IH cross times IH cross will give me IH cross whole square. Then we will have to go with the simple multiplication. So I think I should keep it here. And so what we will obtain here, so our left hand side is Lx, Ly, and psi. So this is going to give me minus IH cross whole square. Okay, then what we will have, we will be multiplying now, and what we'll get y dou by dou z. Okay, minus I would like to write it again, minus z dou by dou y times z dou by dou x minus x dou by dou z. Okay, so I would like to take it away. So now we can distribute. So this is minus, so IH cross whole square will be like this. So what we'll obtain here is y. Okay, so we will have y, then we will have dou by dou z of z dou by dou x. That should be the first term. But let me take psi inside, so it will have a psi here. Then the next thing will be minus y dou by dou z times x dou psi by dou x. No, this is dou z. Okay, this will be my next term. Then the next term will be minus z. Then we will have, I think we can see here, this is z, and this this partial, for this partial dou by dou y, this z will act as a constant, so it will give us z square. And then we will have the double derivative dou to psi by dou y and dou x. Yeah, that's fine. And then plus the final term, because minus and minus will give us plus, that will be z dou by dou y times x. Then we'll have dou psi by dou psi by dou, the last term. So this is z, then dou by dou y of x, then dou by dou y of x, then dou by dou z of psi. That should be this. Okay, so this way, this is our Lx cap, Ly cap psi. Now we would like to we would like to so what we have is we have calculated Lx cap, Ly cap, and psi. Now we would like to calculate Ly cap, Lx cap of psi. So we have to go with the Ly first, then we will go with Lx. So what is our Ly and what's our Lx? So Ly is this much and Lx is this much. So we can write down this as IH cross z dou by dou x minus x dou by dou z. Then for Lx we will have minus IH cross times, then y dou by dou z minus z dou by dou y. Okay, so this is our result for Lx, Ly cap and psi. So it must be frozen into some lines. All right, and now we will have to do the same algebraic evaluation of Ly cap, Lx cap, psi. So on the similar ways, we will have IH cross whole square, and we would like to multiply them. And on similar analysis, what we will do is we will operate this by, we have operated this by psi. We have acted this thing on psi. So in doing so, we can write down this Ly cap and Lx cap of psi. Yeah, we will have IH cross whole square will be out. So what will be inside is we will have z, then we will have dou by dou x of y dou psi by dou z. So this will be my first term, then minus z dou by dou x of z, then dou psi by dou y, and then minus x of dou by dou z of y, then dou psi by dou z, and then plus x dou by dou z, then z dou psi by dou y. So this will be the distribution of the terms, and what we will have here finally is we will have IH cross whole square, and we will have here we can understand for x this y is a constant, so we will have zy, then dou to psi by dou x and dou z. So this will be for this, and then for this we will have z square, then we will have dou to psi by dou x and dou y, and then we will have for this y will come out because the derivative is with respect to the and psi. This is gonna be IH cross whole square, and inside you will have y dou psi by dou x minus x dou psi by dou y. These are the two terms that you will be left with by making the subtraction between the two equations. I failed to be consistent here, but I better understand that you can do it better than me. So on doing this, what we obtain is we obtain this relation, and we can write down this as what is this? This thing is, it has psi with it and it has psi with it. So this thing is the commutation. It is Lx cap comma Ly cap of psi is equal to, I can think of writing here, here it should be minus. So this will be minus IH cross times IH cross times y dou by dou x minus x dou by dou y of psi. And if I write some order here, this is IH cross minus IH cross, then y dou by dou x minus x dou by dou y of psi. Now this thing is nothing but you can see it minus IH cross x dou by dou y minus y dou by dou x. This thing is nothing but LZ. So we can write down Lx cap, Ly cap of psi is this IH crosses out, and this thing is we can choose yes, this thing is LZ. So similarly, we can obtain the commutation between Ly and Lz. And this will give us YZ, this will give us IH cross LX. And we can go with LZ and LX. And this is going to give us IH cross LY. And if you reverse the order, you will be getting the negatives of the results that we have obtained here. And similarly, we can obtain. So, dear students, in this video we will be talking about the commutation relation of total angular momentum. And this total angular momentum is symbolized as J. And this total angular momentum in quantum mechanics, what it does basically, it combines the orbital angular momentum and spin angular momentum components. So in order to obtain the commutation relation for this total angular momentum J, we have to consider how the total angular momentum operator J cap interacts with its components. So if we go with the definition of this total angular momentum, this total angular momentum J, what it does basically, it combines both orbital as well as the spin angular momentum of the particle. So J is L plus S. And the components of this this J operator, we can, if we write down this angular momentum J in terms of its components, we'll have Jx as Lx cap plus L plus Sx cap. We can write down its y component as Jy cap is Ly cap plus Sy cap. And finally, Jz cap as Lz cap plus Sz cap. So these are the components of this total angular momentum vector J. And there exists commutation relation between Jx and Jy, and Jy and Jz, and Jz and Jx. And it's better that I write down those commutation relations and then look for their derivation. The commutation relations that we have is the commutator between Jx and Jy. And what it should come out to be, IH cross Jz cap. Then we have Jy cap and Jz cap. This commutation relation gives us IH cross Jx. And finally, Jz cap and Jx cap gives us IH cross Jy cap. These are the commutation relations between Jx, Jy, Jz, and Jz and Jx. Now, if we reverse this commutation relation, in every case we'll have a negative sign in the right-hand side. Now, what is our aim in this video is that we want to obtain those commutation relations between the components of angular momentum. And to start with, I think let's take on the first commutation relation, and that is commutation between jx cap and jy cap. And we can write down this as for jx we have lx plus sx. For jy we have ly plus sy. So we can write the commutation, we can write the commutator as lx cap plus sx cap, comma ly cap plus sy cap. And we can use the property of commutators. So we'll have commutator properties here, which is purely algebraic. I mean, we will have a commutation between lx cap and then we will have ly cap. This will be the first commutation. Then we will have sx cap and then we will have lx and sy. So let's go by the order. So this is lx cap, comma sy cap. And then we will have sx and ly, sx cap and ly cap. And then finally we will have sx cap and sy cap. So we have the commutation between lx ly, lx sy, sx ly, and sx sy. Now, what we know about angular momentum commutators is what we know is that this lx cap and ly cap, the commutation between them is IH cross LZ. And from spin angular momentum, we have the commutation relation. What's that? That is Sx cap and Sy cap. It gives us IH cross SZ cap. And regarding the orbital and spin angular momentum operators that we have here, orbital and spin momentum operators which commute with each other. What we have in that case, that is L cap and Sy cap. They commute, so their result is 0, and Sx cap and Ly cap is equal to 0. So these two terms will lead to 0, and these two terms are they are going to give us Lx Ly. So what is our left hand side? That's Jx cap, comma Jy cap. This will give us for this we have IH cross LZ plus for Sx Sy we have IH cross SZ. So this is IH cross is out, so we have LZ plus SZ. So IH cross will give us JZ. So what does it mean? It means the commutation between the component of total angular momentum Jx and Jy is simply IH cross JZ. So this is the proof of the first commutation relation that we had. What was that? That was Jx, Jy leads to, it gives us IH cross JZ. Now, moving on to the next commutation relation between Jy and Jz. So we will use the similar mathematical technique. That is what we have now. We have for Jy and Jz. Okay, so here what we can write is we can write it that as Ly cap plus Sy cap, comma Lz cap plus Sz cap. All right, so we can use the property of commutators, and we can write down the commutators here. What we will have, Ly cap, comma Lz cap. Then we will have plus Ly cap, comma Sz cap. Okay, then we'll have plus Sy cap and Lz cap. Then we will have Sy cap and Sz cap. These should be the commutators that will come out of these this commutator. And what we know here again in the similar fashion as we discussed in the past, what we have this Ly and Lz. This commutation gives us minus IH cross LX cap. And SY SZ, what it gives us is minus IH cross SX cap. Then these two, what's that? This is LY and SZ. They commute with each other, and we have 0 for this. And similarly for SY cap, LZ cap, we have 0. That should be the case. So we can move on from here, and what we will get the commutation between JY and JZ is minus IH cross. That will be common. Inside we'll have LX cap plus SX cap. So the commutation between JY cap and JZ cap will give us minus IH cross JX cap. So this is the commutation relation that we have obtained between JY and JZ. And similarly, we would like to obtain the commutation relation between JZ and JX. So let's go with, so the technique is same. So we have JZ cap and JX cap. So what will be this? This will be LZ cap plus SZ cap, comma, then LX cap plus SX cap. All right, so we can use the property of commutators, and we can write down here we will have LZ cap and LX cap. Then we will have plus LZ cap SX cap. Then plus we will have SZ cap and LX cap. Here I had to put a comma. And finally we will have the commutation between SZ cap and SX cap. All right, and again here we can use the commutations for the orbital angular momentum. That we have is LZ, LX. This commutation will give us minus IH cross LY cap. And similarly SZ cap and SX cap, it will give us minus IH cross SY cap. And the commutation that we have is that this LZ cap, SX cap, they commute, so this is 0, this is also 0. So we will have the commutation relation between the components of total orbital angular momentum, that is JZ cap and JX cap. That is going to be minus IH cross LY cap plus SY cap. So this will give us minus IH cross JY cap. So this is how we obtain the commutation relation between the different components of angular momentum, and these relations, the relations that we have obtained for different components of angular momentum, what they reflect is they reflect the fundamental rotational symmetries of quantum systems, and they are essential for understanding the behavior of angular momentum in quantum mechanics. I'm sorry for the mistakes that I have committed in this video in terms of the sign. Here I have used LY-LZ. The commutation between LY and LZ is minus IH cross LX, it's plus. SY-SZ, it is plus. So here the result that we'll obtain for the commutation relation between JY and JZ is going to be IH cross JZ. And again, I have committed another mistake here. LZ, LX, the commutation between these two components between orbital angular momenta, here it is plus, similarly here it is plus, and finally we have plus. So the commutation JZ cap, JX cap is equal to IH cross JY cap. I'm sorry, I have committed this mistake. I hope you will fix it yourself. So dear students, in this video I'll be talking about the commutation relation between the total orbital angular momentum J operator and the Hamiltonian operator. So that's the point of discussion in this video. And the commutation that we have, the commutation relation between J, which is total angular momentum, and Hamiltonian operator H, it is an important aspect of quantum mechanics, particularly in systems in which you have rotational symmetry. Rotational symmetry. And in order to have this commutation between J and H, what we assume here in this case is that this Hamiltonian H that we have, this Hamiltonian is invariant. This H is invariant. It is invariant under rotation. And what it means, literally, it means that it commutes with total angular momentum J. And let's go with this problem and try to have some discussion on it. So if we have to write down the total angular momentum operator J, what it is basically, it combines, it's a result of, it combines both orbital angular momentum and spin angular momentum. And this L is over, this is the orbital angular momentum operator, and this S cap is the spin angular momentum operator. And the components of this J are, if I write down Jx cap, that's going to be Lx cap plus Ly cap. Jy cap is Ly cap plus Sy cap. And then Jz cap is Lz cap plus Sz cap. And what's our motivation here? What's our intuition here is that we want to talk about, we want to obtain this commutation between J and H. And what is that? This J commutes basically with the Hamiltonian H. So JH, the commutation between J and H is equal to 0. And so what does this relation state? This relation states that the total angular momentum J, it commutes with the Hamiltonian, which means or which implies that this angular momentum that we have, this angular momentum is conserved. If this Hamiltonian, this H, if this Hamiltonian is rotationally invariant, So, assuming this H is invariant under rotation, which means it does not change when the system is rotated. You have a system, you rotate it, and this Hamiltonian does not change. That's what's meant by rotationally invariant. So we are assuming this Hamiltonian to be rotationally invariant, means it does not change when the system is rotated. So what we have, J cap and H cap is equal to 0. Now, to come up with the reasons for this commutation, if I take the commutation relation between, say, Ji and H cap, this is equal to 0. Now this I goes for x, y, and z, the three components of this total orbital angular momentum. So we can think of writing the commutation between replacing I by x, so jx and h. And we can expand it for jx. What we have lx cap plus sx cap, and comma, we have the Hamiltonian. So here, what we'll be doing is we will be using the linearity of these operators. So we can write down this commutation as an expansion. So what will be that? That will be Lx cap, H cap, and then we'll have plus Sx cap and H cap. And similarly, we can write down Jy and H and Jz and H. So for Jy, we will have y components replacing the same relation. For Jz, we will have the z component replacing the same equation. So if H that we have been talking about here if this H is rotationally invariant, if it is invariant, what it means is that this H is symmetric. It is symmetric under rotations. Therefore, H should commute with the components of the angular momentum, because H is symmetric under the rotation. So we can immediately write down, we can, because they will commute. I mean, if this L, the component of orbital angular momentum, will commute with H, and the X component of spin angular momentum will commute with H. So this should be equal to 0, and this should be equal to 0. And what we will have? We will have the generalization. I mean, we know that this Lx, it commutes with Hamiltonian. Similarly, Ly commutes with Hamiltonian. Similarly, Lz commutes with Hamiltonian. So we'll get 0 in all these cases. And in the similar way, Sx and H will commute, and Sy and H will commute, and Sz and H will commute. So we can combine all of these results. So we will have Jx cap and H cap. This is going to give us 0. And what we will have Jx cap and H cap. This will give us 0. Then Jy cap and H will give us 0, and Jz cap and H will give us 0. Right? And what does that mean now? Therefore, we can say the combination of the commutation relations that we have between the total angular momentum components Jx, Jy, and Jz. These are the commutation relations between the components of angular total orbital angular momentum. And this result confirms, what it confirms is that if H is rotationally invariant, that means on rotating the system, we have symmetry. The system does not change. Then the total angular momentum vector, which is J, this J commutes with Hamiltonian H equal to 0. It means that this J, what's called as total angular momentum vector, is conserved. It is conserved. And that's it.